Okay, so the smallest set of linear independent system variables such that the values of the members of the set at time t naught, at this time t naught can be any time, or this t naught could also be equal to 0. Okay, along with known forcing function. By forcing function I mean to say the input to the system. Just a minute, what is this? Okay. Completely determine the value of all system variables for all t greater than equal to t naught. So state variables basically plays a very important role in this representation, because from this definition, the other implication of this definition is that state variables are nothing but equivalent to capture the memory of the system, let's say at time t naught, if I am specific to time t naught. Okay, it basically captures the memory of the system at time t naught. Meaning to say, if I have the knowledge of the system variables at time t naught, and those system variables should be linear independent, okay, then I can completely determine the value of all system variable in the for the future. This is what I define the future t greater than t naught. Then the space, which is formed by the state variables, we call it the state space. And similarly, the state equation, a set of n simultaneous first order differential equations. So this is the key part here, the first order differential equations with n variables. And we will come on to the state equations and the output equations. And output equation is nothing but a linear combination of system variables and the inputs. So this is what I mean by the state space. Let's say I have two states. I have defined these two states, x1, x2. Now important point to note here is that these state variables are basically defined by the users. Okay, because in the definition it says I just need to, so yes, I will come on to this physical significance. So these I need to find only those state variable which forms the smallest set of the linear independent system variables. Okay, so the physical significance of the state variables is basic, like I said, that it basically captures the memory of the system. Okay, so because memory is pretty much important to compute the values for the future. Now, knowing the values of the state variables at any time t naught, which could also be 0 or the initial conditions, then I can compute the value of the system variables in the future. Because so you can also understand this value of this state variable at t naught as where t naught could also be 0 as the initial conditions. And while doing the uh, Laplace analysis, we had seen that how important the role of the initial conditions are. We need how we can differentiate between the 0 minus, 0 plus, and the continuity and discontinuity. Okay. So I was talking about this state space. So let's say I have defined two state variables, x1 and x2. So this point, let's say this particular point would be my x1, excuse me, x1 comma x2 at some t is equal to or t1. I won't use the word t naught. Let's say at some time t1. Okay, now in whatever way this point, which is basically a state vector, traverse in the whole space give me the state trajectory. So the overall space, this one is the state space, x1 x2 are the state variables. A point on the let's state space, a point on the state space would give me the state vector. Now the traversing of this state vector in the state space would give me the state trajectory. Okay, so this is how you can visualize geometrically how the state space representation works. Okay. Now come to these two main important equations. So the first equation, we call it the state equation, where I have x dot is equal to ax plus bu. Now if x is my vector, where x the vector, let's say x is a vector of two dimensional, let's write it x is equal to x1 x2. Okay, x is equal to x1 x2. Now in that case, where my x, let's write is 2 cross 1. Okay, in that case my A would be a matrix of 2 cross 2, because x dot would also be 2 cross 1, x is 2 cross 1, so I would have A as a 2 cross 2 matrix. Now suppose if I have u as a scalar variable, in that case if u is my scalar, let's say u is a scalar, in that case my B would be 2 cross 1, so that all the dimension matches. So u is my input, x is my state variable, and this last equation we call it the output equation, which is nothing but a linear combination of the state and the input variable associated with two matrices C and D. Okay, so this overall representation gives me the state space representation. Now the beauty of this state space representation is that this is a generic representation, and in this representation you only see the single derivative, which is dx by dt. So one significance of this state of this representation is given any higher order differential equations. So if we see the path, let's see, if I see the path differential, maybe I can write below, yeah, here I have found space. So I have some this differential equations. Okay. Now this, from this differential equation we go to form the transfer functions by using the Laplace transform. So if I have nth order differential equation, then I know, or we had seen that by taking the Laplace transform I would obtain n degree polynomial in the denominator of this transfer function. Okay. Now from this differential equations I can find the state space representation, which would be of first order differential equation. Yeah, here we write nth order differential equation, and here I will write the state space representation, which is of first order differential equation. So this path, because if I have the first order differential equation, then it is easier to analysis the other aspects of the system. Okay, so we will see that from so in the rest of the notes you would see that for the given circuit how you can write this compact state space representation in only by using the first order differential derivative. Okay, so I would suggest you to first go through this example. Take this simple circuit where we have the RLC circuit. Hmm. So write the complete differential equations what you have done earlier. So here you have two loops. First is this loop, second is this loop, and you can write the differential equation. Okay. Now from that differential equation you would see that this would be a second order differential equation. Okay, and then write the transfer function of those differential equation. You can take uh, let's say output as IR, output variable as the current flowing in the resistor. Okay, so you can write the transfer function upon IR as Vs transfer function, and similarly the differential equation, and then see these equations what I have written here. So I have chosen the state variables as x1 x2, the voltage across the capacitor, and the current flowing in the inductor. So I have chosen these two state variable Vc and IL. Now to finally obtain these equations, I have written all the equations and finally assemble them in such a way so that I can get the derivatives onto the left hand side. Okay, so here we have Vc dot IL dot hmm, these are my state, the derivative of the state variable. This is my A matrix. Sorry, this is my A matrix. This is X. This is B, and this is U. U is my V. Right. Here I have the output as Y. This is my C matrix, and this is again my X, which is Vc and IL. And here I have D is equal to 0. So this is 0 dot Q. Okay, so go through this example to finally obtain this state space representation. Okay, so I think we can stop here today because there's a lot of thing for you to study by yourself also. But this is the overall idea that uh, given the differential equations, which is basically the core part of capturing the dynamics of the system. Hmm? From there we have seen this path by by taking the Laplace transform. I can compute the transfer functions. So this is one way of doing the modeling. Another path is from this differential equation. So just to mention that this is a frequency domain. Okay, this is time, and this is whole analysis is in time domain. Okay, because if you are doing the analysis in the time domain, then you do not need to worry about the 0 minus and the 0 plus. We had seen earlier also. Okay, so I would suggest you to uh, try to solve those problems and given in the tutorial problems, and go through the notes as well and the videos. I know that the video which I have found on the NPTEL course page is a bit long, but you can skip most of the portion because that professor is taking a lot of examples. And in the book chapters also, I have uploaded two book references Just a minute. Let me. So these are the excerpts of some book pages from two books. One is from Kuo and another is from Norman Nice. So I've specifically selected some pages of the book which you can follow. What is it? So how to solve for state space by an SFG or a block diagram. So so this is the path which I suppose is covered in the page 19 of the lecture notes, where we go from the state diagram to the state space equations. Okay, so the whole procedure has been explained here in using the signal flow graphs. So I suggest you to go through the example, and then we can see in which specific point you face difficulty to proceed further. Okay, here we also have the trans function from the state space. But how to choose the states by an SFG? By an SFG, we also select the state. hmm. Say for example, if we are given any differential equations. Okay, so I will come on to this path. Okay, I will come on to this part where we have defined the complete summary. So this differential equation, from this equations you can form the state diagrams. Okay, now in the above text, two procedures have been listed: the state space representation and the transfer functions. So choosing the state variables, here we have explained in the steps. Okay, I will suggest you to go through the tutorial problems and see if you are able to visualize by yourself selecting the states. Okay, so there was another question which I had missed. uh, if we can only model linear equations, then how do we model non-linear systems? Okay, so this state space representation is is basic is specifically we have used for the linear systems. Hmm? Now if we want to model, let's say, the I will not go directly onto the non-linear systems. This is, but let's say, let's take this. Okay, so I have this x dot is a x plus b u. Okay, y is equal to cx plus du. Okay, now if a b c d matrices are constants, then it will be a linear system. Now uh, if by model description I have these state matrices are not the constant matrices but as a function of time, then it will become the time varying system, but and at the same time it would still be a linear, because it's a linear combination. Okay, now there could be another representation. Let's say instead of this t I have the as a function of states, then it would become a nonlinear system. So if I speak in general, the generic description of a state space representation for nonlinear system is given by x dot is equal to some function f which is the function of x, u, and let's say t. Similarly, my y would be a function g, which is again a function of x, u, and t. Okay, so this is the generic representation of any system. Now if my this map function or f and g are linear with respect to the system variables, then I will have the linear systems. And if it's some non-linear combination, then it would describe the non-linear equation. Here this f is a vector value function. Okay, vector value function in the sense that if I have my x as x1 and x2, then in that case I would have my f as two functions f1 and f2, again as a function of x, u, and t. And similarly goes for the g. Okay, so this is how I can represent the nonlinear systems basically. But we won't be discussing much about the nonlinear system, because in the next week we will discuss about the linearization, that given any nonlinear system, how we can obtain the linear system. Okay, so this is about some description of the state space. What is the meaning of these a b c d matrices? What is the meaning of the state variables? How you can represent the same set of differential equations into another representation, which we call the state space, which is analogous to your transfer function in the frequency domain. Okay, so here in the next couple of pages you would see again the representation in the signal flow graphs and the state diagrams. Okay, and in some yeah, so we'll see in the next online meeting if there are other aspects. Okay, so if you have some related question, then we can take them now, or I can let you to to go through some examples and solve the tutorial problems. Okay, so I think we can stop here for today. Mm-hmm. Yes, Manas. So how to choose the states in question 2 of tutorial? So I said like I said that you can choose any states. You can choose any variables as the states, whether they make some physical significance or whether they do not. Okay, but it is good, or it is much more of significance if it has some physical uh, significance in the given system. Now here in the question number 2, only the block diagram representation is given to you. So first of all I would suggest you, I think I can, let's open this thing. Yeah, I think there is some problem with the connection. Okay, but we can see. Okay, I can take it here. So first of all, what would I suggest you, that for this tutorial problem, if you have it open in front of you, that first of all write the complete transfer function ys over us. Okay, because this is a feedback configuration, and in the forward path you have a third order degree transfer function, third order transfer function, because of the multiplication of the first order and the double integrator. Okay, so once you have obtained this transfer function, um, so here in this step, okay, so transfer function to state space. So in this section I have explained that how you can obtain the state space, the state variables. Okay, do you get this point? That first of all, for this block diagram, obtain the transfer functions from u to y, the complete transfer function, because u and y are the external variables, and they are pretty much fixed at the outset, that what would be my input to the system and what would be the output of my system. So these are the physical variables, or I mean the having some physical significance. Now, and these map or this mapping, let's say u to y, hmm, this mapping u to y could be a higher order differential equations. So the idea is to choose some internal variables which we call the states, and using those internal or the auxiliary variables, I come up with this compact representation where I am computing only or using only the first order derivative or the first derivative instead of using the higher order derivative. Okay, so first of all, try to obtain for different examples or different problems either from the textbook state space representation, just to get familiarized with the ABCD matrices and with the notations also. Okay, and then we will see that how you can solve those equations as well, and then other properties uh, associated. No, I would not say this, that you have to find that transfer function first, particularly for the problem number 2. All the differential equations are not given to you. If we see to this path, this summary, if you see this summary, that only the transfer functions are given to you. Yes, in this problem, yes. So in for this particular problem, you have to compute the transfer function. But if the differential equations are already given to you, then you can also obtain the state space representation. So just to mention, for those who are wondering, that in this summary I have specifically written two more terms, LDS and nonlinear, and IPC and robust. So the idea was to connect all these blocks with some other future courses what we are running in the control group. So here we, in this course, we will see only the basic introduction of the state space representation and do some basic analysis. Okay, but then exhaustive analysis of these representation we will see in the linear dynamical system course, which is EE509. It's just for the record, so that if you are interested later, then you can see. And there's another course, nonlinear system, which is EE514. Okay, so in the nonlinear course we will study the nonlinear description, and we will also see their modeling in the state space, and this linear dynamical system only concerned with the time varying and the time invariant part. Okay, now by using the transfer functions, we will see the the major role in another course, what is industrial process control, IPC, which is a sixth level course, and this robust control course, which is E. Uh, you just verify either it would be 515 or 514, and similarly 514 or 515, huh? It just verify it if you want to see it later. Okay, so we'll take these transfer functions and do a more exhaustive analysis by in these advanced level course, and similarly for the state space representation. Okay, but for the moment, okay, in this course you would get to know all the tools, all the broad tools which are basically useful for the system analysis, hmm, and get acquainted with their basic analysis. Okay, so this is the overall idea. Yes, so anything else? I think we can stop here today and let you study and the other parts of this week, and then we can so this nonlinear systems, I think, yeah, we will cover in the next week about this linearization. Okay, yes. Okay, so if you have some questions, then you could ask. Otherwise, we can anyway take them on Thursday once again, once you have covered uh, a major portion of this week's topic. Okay, so you can start disconnecting and then I will disconnect likewise we have done in the last week.